Success. I'd like to present some of the results today of the Kepler mission. The Kepler mission was designed to find out whether Earth-sized planets are common in our galaxy or rare. If they're common, there may be a lot of life. Life might be ubiquitous in our galaxy. If uncommon, we might be alone. I can assure you that there are lots of Earths. So let's talk about some of the results. Now, part of the results that we get from Kepler are not just trying to tell us about Earth, but they're basically giving us information for future missions. Because Kepler is just a probe, the first probe that could find planets and habitable zones. But we're going to want to do a lot more than that when we find these planets. So I'll talk a little bit about the future missions that will be using some of the data Kepler has developed. I always like to start out and talk about how planetary systems form. We know that our galaxy is full of giant molecular clouds of dust and gas, that every so often they get disturbed, and a supernova goes off, for example, compresses part of these clouds. That causes a gravitational collapse of that portion of the cloud. It maintains its angular momentum as it falls inward, so it ends up as a flat, fast-rotating disk of dust and gas. And that basically forms the star and the planets at the same time. So expect to see every star having planets. When we look at this rotating disk, we can see that the planets are all going to form in the same plane. They're all going to go in the same direction. The plane of the planets is going to be perpendicular to the spin axis of the star. We're going to expect that in toward the star, we're going to see hot material. The only thing that we can condense out are refractory materials, so we'll expect things like Mercury, Venus, Earth, Mars. And further out, the gas is much cooler, and the circle is much larger for the planet. It's got more mass to build itself, to build a big mass. It can bring the ices in and get massive enough to bring hydrogen and helium in, and you can build giant planets. So that sort of explains our solar system. It doesn't completely explain what we have found, however. And in particular, we do find big planets in short period orbits. And the thought here is we have to add to this picture, and basically that addition is that the planets move. They move quite a bit during the formation process of a planetary system. And we'll see some of that with what we have found. Well, the Kepler mission is a telescope in space that operated for 4 years, took data for 4 years, and we're in the process of reproducing that data. It lost 2 of its reaction wheels, so the data that I'm going to talk about is now collected. We have all that we're going to get, and we're analyzing that. There is a mission built on that telescope called K2, which is also looking for planets, but it does not have the precision that the original mission does, and it cannot look in the same direction. When you think about what we're doing, which is looking at a large number of stars simultaneously with the telescope, measuring the brightness of each of these stars, you see a lot of stars. You see 170,000 stars. So we learn a great deal about the stars, and in fact, very many papers talking about what we've learned from these stars is available in the literature. But just to give you a feel for what's out there, I've shown the sun in the upper right there. That's our sun. That little speck is not a fly poop. It's a planet orbiting, transiting that star. That's a Jupiter-sized planet. We're interested in planets 10 times smaller, 100 times smaller area. You can see the stars here that we look at are immensely bigger than the sun, and many of them, from the bottom you can see, are quite a bit smaller than the sun. So I'm going to tell you a little bit about some of the star situations that we found before I talk about exoplanets. Here's an example of some of the data that we obtained. If you look at the upper right, you can see that we're talking about, tens of parts per million, 50 parts per million, and we see this little jitter on the top. That's the variation of the stars, of that particular star that we're monitoring. We're monitoring its brightness. we're doing this, as I say, at 170,000 stars simultaneously. It's sort of a big camcorder. And what you notice is there's some spikes that occur every so often. Those spikes are the transits. The object transiting this star is blocking some light. And so we can add that data up at the right phase so we see the transits all lined up and get a very low noise signal. If you look at the bottom, this one. If you look at the bottom curve here, here's the brightness of the star coming along, dips down and comes back up. And it's roundish on the bottom. And that's because if you look at a star or you look at Jupiter, what you see is it's sort of dark along the edges. That's because it has an atmosphere. If you look at the moon, at full moon, it's flat. It doesn't show that. So this is definitely what you're expecting for a planet transiting or any other object transiting a star. Now, that dip tells you this object must be about the size of Jupiter, 8/10 the size of Jupiter, 8 times the size of the Earth roughly. So we know the size, we know the orbital period, and usually when a planet goes around the back of a star, we don't see any change because it's reflected light and the emitted light from the star in front of the planet is trivial compared to that of the star. But in this particular case, here's what it looks like. The light from that group, the object and the star, dropped down very fast and was flat. So it went behind the star. That change in the brightness, the radiation, you can use to calculate sigma t to the fourth. You know the area here from this transit. So you can calculate that the star, this object orbiting it, is about 12,000 Kelvin. The star is 9,000 Kelvin. So clearly when we found this, we were astounded. We just couldn't imagine what this was. Could it be that the cool star was heating the hot planet? We have a new law of thermodynamics, but nobody wanted to write that paper. So we asked, what else could it be? But the thing that jumps into mind is, watch it, it's just a white dwarf. You're seeing a hot white dwarf go behind your star. But we all know how big a white dwarf is. The size of the Earth. We've measured it. It's 8 times the size of the Earth. So what could this be? Well, we're not sure. It may be just a big white dwarf. It might be that what we're seeing here is an unusual stellar combination. And that is, you could start off with a binary star. Half of the stars in the sky are binary. And one of them is more massive than the other. It burns through its helium, its hydrogen very rapidly, expands into a giant, but there's a star near it. It's a binary star. So that sweeps up all this extra gas and becomes massive itself. So all you have left then is a hot, naked core of the first star and this other star at 9,000 Kelvin. So there's all sorts of possibilities, and we see a huge number of interesting objects when you're looking at almost 200,000 stars for 4 years. Here is another event that we found. Now, instead of the light going down regularly, it goes up. Now, what could that be? Well, what we thought at first was this was a black hole orbiting a star. And so we see microlensing. The hole goes in front of the star, the gravitational force pulls the light around, and we get a brightening of that star. So we asked our colleagues to use the X-ray telescope and look for X-rays. They found no X-rays. We also went to the telescope and got some spectra. And what we found was that this was a pair of A stars, which are bigger, hotter stars than our own Gstar. And usually when stars orbit each other, they're orbiting in a circle, or maybe it's a little bit elliptical, but these stars are an extremely elliptical orbit. To us, it almost looks like it goes up straight out and comes straight back in. It comes hurtling toward each other like a couple of kids in a bicycle playing chicken. And the mist is just so small. It's the diameter of a star. So those stars, as they come toward one another, aren't spherical anymore. They become football shaped as they point at each other. And we see all this extra light. And then as they hurl by, they jiggle. We see waves passing through their surface, and you can see the wave structure here and the pulses here. Very regular. And we see a fair number of these rather strange objects. Well, my talk is mostly about exoplanets. I like to talk about exoplanets. We see something of the order of 100,000 things that might be considered possibilities. When we look at these carefully, and we say, well, the transit duration has got to be proportional to star diameter and inversely proportional to how long the planet takes to orbit the star. So you can calculate what that duration ought to be. You can calculate other aspects of how that transit should look. Only about 4,000 of these objects meet that criteria. So we have about 4,000 candidates that we have every reason to believe are planets. And we call them candidates because you have to, it's important to verify that they really are planets. Otherwise you come up with the wrong numbers and you come up with poor estimates of how frequent such planets are around other stars. And to do that we use large ground-based telescopes. Most of the large telescopes on Earth have been used in one fashion or another to do confirmation. We've confirmed about 1,000 of these objects. I'm going to show you the sum of all of those and talk about their characteristics together. But only 1,000 of the candidates have been fully confirmed. This, in fact, is the data on most of the exoplanets. The various groups here on the Earth have found about exoplanets. You see the horizontal axis is orbital period, 1 day to something like 100,000 days. And the vertical axis is how big are these exoplanets. You have Earth there, 4 times larger as Neptune, 11 times larger as Jupiter, and then objects even bigger than Jupiter. The yellow data is the data that we have obtained. And of course what it shows us is a huge number of planets that are between the size of Neptune and the size of Earth. And in fact there are many smaller than Earth, many the size of Mars. We find planets as small as Mercury. We find some planets almost the size of the Moon. And we suspect that the reason we don't see things smaller is because those things get lost in the noise. The blue objects here are objects found with radial velocity work. They tend to find the bigger planets, usually bigger signals, and they've been at this for about 20 or 25 years now, and so they're seeing the very long periods. The area of interest, of course, is that line at 1 Earth size, and with orbital periods of about 365 days. But we can see we find very little there. That's simply because we need to look longer, and we need to look at our data more thoroughly to find some of these objects, because they are buried in the noise. It's our job to pull them out of the noise. The red dots there are what people find from microlensing. That is to say, if you have a ground-based telescope and you're looking at the center of our galaxy, there's a huge number of stars together. Those stars are shining light toward you, and if there's a star in between you and one of those stars, particularly if it's a red dwarf, the red dwarf is by far the largest fraction of stars in our galaxy, then the light can come around the red dwarf and get focused to you. And so what you see is the background start brightening up for a period of a few weeks. Sometimes there'll be a little glitch on that curve. That little glitch is a planet. And so it's a way of finding planets. And you can see the microlensing people have found some planets, and they actually have a mission that will be launched to do this in a much more thorough fashion. So we'll look at some of these characteristics of these planets next. Well, let's first of all, in fact, look at numbers. Science is about numbers. Earth size, we found about 700 Earth-sized planets. That is between 1 and 1 1/4 the size of the Earth. About 1,100 from 1 1/4 to 2 times the size of the Earth. And about 1,500 planets that are about the size of Neptune. But the first two groups are the important group. And that is, they are small enough so that we don't think these are gas planets. We think most of them are probably rocky planets. Planets you could walk on. Planets that might have atmospheres that could conceivably have life. So these are the planets of most interest to us. But we see some 1,500 Neptune-sized planets. Jupiter planets are much more rare, and even planets larger than Jupiter, rarer still. Which is interesting because, of course, it's easy to find the big planet with the big signal. hard to find a small planet, and yet we find a lot of small planets. And in fact, we know we miss a lot of small planets because they just get buried in the noise. We don't see enough transits to come up out of the cylinder, come up out of the noise. So this is what we call the observed distribution of planets. What we really want is a parent distribution, the actual distribution of planets around stars in our galaxy. So we have to compensate for the various biases. One of the very obvious, one of the very big biases, of course, is the fact that in transit, the planet has to pass between you and its star. What's the probability that's going to happen? Because these planets are all oriented in an arbitrary fashion around these stars. The answer is what's proportional size of the star divided by the size of the orbit. For short period orbits, 10 days, a week, a couple weeks, that's about 10%. So if we see a planet with orbital period of about 10 days, we've missed 9 out of 10. But that's great. We can calculate that. We know how big the star is, we know the size of the orbit, we can correct for that. You're saying, well, I want to know about stars or planets in the 1 AU. Well, the miss is about 99. You'll miss about 99. So now you compensate by a very large factor, a factor of almost 100. So we have been doing those calculations, calculating how many we miss, calculating how many are false positives, and doing this geometrical calculation. The work is still very preliminary, and when you look at the literature, you're going to find a number of values, but our best value is shown next. And what you see here is the curve of the planet size versus how many per star. And what you see is Earth size is by far the majority of them. The correction for the fact that we miss a lot of small ones is very large. We're seeing something here about 4/10 or 5/10 of all the stars have an Earth-sized planet. 20% something, again, that might be a rocky planet, a super-Earth, we call them, and then the bigger planets. So that implies, of course, that our galaxy is full of small planets. There'll be lots of places to consider going to if we ever have spacecraft that does 10C. Okay, we find a lot of planets, the ones that are easiest to find, the ones that are closest to the star, because the geometrical probability that you'll see that transit is very high. So here is one such example of what we found. It's an object that's orbiting its star. Its year is something like 15.7 hours. It goes around every 16 hours, very close to its star, and consequently it's very hot. Its temperature is some 2100 Kelvin, and that's very hot. If you put your foot in molten lava, you might get to a temperature of 1700 Kelvin. If you were to touch molten iron, it would be 1800 Kelvin. This is hotter than that. This planet is evaporating. And in fact, it's 1 over E lifetime is some 200 million years. So we see a lot of strange objects like this one. Here's another one. This one's about 1.5 times the size of the Earth. Again, its orbital time is something of the order of 17 or 18 hours. We were able, because it goes around so rapidly, to not only get its size, but get its mass or rate of velocity. So now we have its density. Its density here is about 5.8 grams per cc. Water is 1. Earth is 5.5. So this is denser than the Earth. This is probably a planet not that much different from Earth. Iron core, silicate rock, a mantle. But its temperature, again, is 2100 Kelvin. So very, very hot. If it's a silicate surface, you're looking at a molten lava surface. If it's an iron core system, you might even have ocean of iron. When we think about planets orbiting stars, we think about the fact that the spin axis of the star is going to be perpendicular to that plane of orbits. When we can measure that, we can test that hypothesis. And what we see here is a method and an example of a situation where the orbital plane of this planet is not lined up perpendicular to the spin axis of the star. The way this is done is you can see, first of all, we see a transit. There's our nice transit, brightness like this. But we also look at the spectrograph and say, what do we expect to see from that spectrograph when the planet goes across the star? Well, if it went across this limb here, well, that's blocked some blue light, so the star will appear redder to the spectrograph. As it comes across the other side, it blocks some red light or some blue light, and it becomes the other color. And so you expect the spectra here to jump up, go past zero, jump back down, and continue on its way. But that's not what we see. What we see it jump up, so it's crossed this limb, but it didn't cross that one. It came down near the pole. So we can determine the axis, or the inclination angle here, between the plane and the spin axis. We call the obliquity. And about 20% of the planets we find, in fact, do have offsets like this. So it's telling us there's something changing the orbits of some of these planets. We believe they form in that disk. And the belief is right now that when the planets are forming, they can get fairly close together and influence one another in such a fashion. One changes its ellipticity, and the other one begins to move the axis up near out of the plane of the orbit. And then, of course, this is repetitive, and so it comes back down, and the eccentricity of the other planet changes. So very different planetary systems than we think about in our own solar system. The other thing that we think about is that if the planets form close to the star, they're refractory. They're rocky. They are like Mercury, Venus, Earth, and Mars. If they're far out at Jupiter's distance, they are gas giants, like Jupiter. But here are a pair of planets that we have found that are extremely close in terms of orbital distances. Their semi-major axis is within 1/100th of an AU of one another. That's the diameter of a star. So you think immediately, well, surely then the planets that are roughly the same size will have the same densities. They'll be both rocky, or they'll be both gas. If you look at the upper one, the chart there says that it's 1/2 times the size of the Earth. Its density is 7.5 grams per cc, so it's denser than Earth. Iron, by the way, is 8, so it's getting close to being an iron ball. Here we look at the other planet, 0.13 AU instead of 0.12 AU, and its density is 0.9 grams per cc. That's less than 1. That's less than the density of Jupiter, which is a gas giant. That's about the density of Saturn. Two objects very close to another, completely different composition. So it's telling us again, our planetary system, our ideas have to be revised. Almost certainly the planets moved from where they were formed toward one another and came into this stable situation here. We don't understand how that could happen, but we do understand how planets can move. When you go out some night with your girlfriend or your boyfriend, and you wish upon a star, about half of that time, that star is really a double star. Maybe sometimes a triple star. And the question is, since half the planets, half the stars in the sky are double stars, do they have planets? Theory was that probably not long ago, but they do. They do have planets orbiting them, and this is one such planet. We named it Tatooine because it was the first planet that we found that orbited a pair of stars. It's called corrected here because if you'll notice, the big star is white, small star is red. Now, in Sky Wars, the colors are reversed. So we called George Lucas when we found this and said, George, we think you made a factual error in your Star Wars. he wasn't horrified. But he did send his team out as part of the press conference to learn a little bit more about planets around binary stars. So this question is this the home of Luke Skywalker? We can see from the temperature, minus 126 Fahrenheit, it is really cold. Antarctica is very warm compared to Earth. So this is not good farming territory, so we don't believe George Lucas. Luke Skywalker lives here. We have to continue our search. Here is another pair of planets orbiting a pair of stars. But this planet is in a habitable zone. And that's great. Could it be his home? The answer is no, it's too big. It's bigger than Neptune. So it's not a rocky planet. It's almost certainly some soup of hydrogen, not helium, and maybe about a rocky core. So he doesn't live here. But what about moons? Massive planets like this could have moons that orbit them. Those moons could have the mass of Earth. That would be stable. That would have an atmosphere. Maybe avatars live there. Maybe this is Pandora. We don't know. But we're searching for these moons because we expect these massive planets to have moons. And so we haven't found any yet. We have found some signals. The signals ultimately proved to be noise. But we continue to look. We need something smaller if we're going to talk about habitable planets. And this is the first planet that was reasonably small that we found a habitable zone. It's about 2.4 times the size of the Earth, so it's probably not a rocky planet. But is it a Neptune planet? Neptune's 4 times the size. This is 2.4. In fact, many of the planets that we find are about this size. This has no analog in our solar system. There's nothing like it in our solar system. It's probably not rocky, it's probably not gaseous, it's something in between. Theoreticians say, one of the things it could be is it could be a water planet. That would explain its density, its size, and so you would have this planet with a very massive core of ice and water and water ocean on top of a steam atmosphere. So it's not cool water like we're expecting, but steam. Could life be there? Well, we know in the subsea vents, where water comes out at temperatures well above boiling, there's lots of life. So this planet, in that case, might have a lot of life. And life evolves. So you could imagine, if you've got a good imagination, that big objects, big creatures, eat little creatures. And the little creatures don't like to be eaten, so they evolve, and maybe some will become flying fish, so they can fly out of the ocean, avoid the predators. And of course, if they're really smart, they learn to fly well enough, so they never have to land back in the ocean. And so you could have creatures. I have an ocean with creatures in it, and an atmosphere with flying creatures. Who knows what's on this planet? But it is in the habitable zone. It's probably not Earth-like, so we need to go on. Here is a system where we have found 2 roughly Earth-sized planets. They're super-Earths called 62E and F. The habitable zone here is shown in green, where you could have liquid water on the surface. And that green area is quite small compared to the one for our solar system. In our solar system, we have, of course, Earth and Mars. In the habitable zone, Venus almost makes it. In this other zone, we have 62E and F, 1.4, 1.7 times the size of the Earth. Again, probably rocky planets in the habitable zone. But you look at the image here, the star is smaller than the sun. It is not the size of the sun. It's about 2/3 the size of the sun. It's cooler. It's called K-dwarf. So we still haven't found our Earth around G-dwarf. So let's look again. Here's a planet almost identical to the size of Earth that we have discovered. It too is in the habitable zone of its star. But if you look at the size of that green zone compared to the solar system, it's very small because it orbits a red dwarf, a small star about half the size of our sun. But it does have a planet, Earth-size, in its habitable zone, and in fact, its temperature is probably very similar to that of Mars. It's rather chilly. This shows a lot of our candidates, a lot of the candidates that are in the habitable zone. Here we have the flux received by the planet. So this is the heat flux. This is what drives the temperature of that planet. And 1 is essentially what the Earth gets at 0.3 or something like that, what Mars gets. And we have on the vertical axis the temperature of the star. Our star is around 5,700 Kelvin, and so in fact, if you look at that temperature range here, you see Venus and Earth and Mars, 2 in the habitable zone. The green area moves a little bit with the temperature of the star. As the star gets redder, more of the radiation actually gets to the surface, heats it up better. Skies wouldn't be blue any longer because the scattered light wouldn't be there. There's no blue light to scatter. We have 22b, which is the planet I talked about that might have flying fish. We have 62e and F, and we have the smaller ones here. And these are other candidates that we are examining. We're trying to understand their stars so to better understand their sizes and their temperatures. So we have a lot to look at. We have the order of 50 or so candidates that we're examining that are in the habitable zone. Okay, so let's summarize some of this material. Most stars have planets. Earth-sized planets are common. But we haven't found an exactly Earth-sized planet in a star just like our sun yet. We continue to look. But let's think about what those numbers mean for a moment. Most stars have planets. There are 300 billion stars in our galaxy. So 300 billion planets. Maybe 10% of those stars are G-dwarfs. Maybe 10% of those have a planet in a habitable. Maybe 10% of those are Earth-sized. So those are the sorts of numbers that we get. Well, so that's about something that are a billion Earth-sized planets, habitable zone, a star similar to ours. Well, why haven't we heard? Why haven't we heard from all those planets? Why hasn't there been a signal picked up by SETI? SETI looks and looks extremely capable equipment. It's found nothing. And so that's really a question that a lot of people are asking. Simple answer, it might be that we're looking at the wrong frequency, the wrong kind of transmission. That's a guess. But other people are asking themselves, well, maybe it's more subtle than that. It may be that it's very difficult for life to arise. We think, because it arose on Earth, that it will arise on Mars, it will arise on other planets. But maybe that's not true. Maybe it's very difficult to get exactly the right conditions to start life. And consequently, we don't hear from anybody because there's no one out there, or very few out there, or their civilizations last a certain length of time and then disappear. Or maybe there's a different kind of challenge. A challenge where it's easy to start life, but as life evolves, it runs into some challenge that it cannot meet. Maybe it's there are people who get very good at building nuclear weapons or biology systems that are mutating viruses, and they disappear. We don't know what that answer is. Certainly when we explore the planets and we see lots of life, something like that. If we see the remnants of lots of life, it's a warning that we may be facing other challenge yet. But whatever it is, there are a lot of planets out there, and the fact that we don't hear from them is very significant. Let's go and talk a little bit about the future. There are quite a few missions that are being designed. Some of them are being built right now to go and tell us more about what's out there, what sort of planets are out there. TESS and Plato will fly in a few years. 5, 10 years, depending on which of those two. TESS should fly in 2 years, Plato in 2025. And they will be looking, not like Kepler, which looked out as a single probe to find out, are there planets out there? But they'll be looking at a star closest to the Earth to see if we can find which of those stars has planets. Then we want to look at those planets, and JWST will look at some of them, although JWST will not be able to find atmospheres or measure the properties of the atmospheres around planets like the Earth and habitable zone. It will give you interesting information about the composition of atmospheres, but probably just the giant planets and in nearby orbits. We're going to need to build a telescope beyond JWST, something called ATLAS. I believe that's an acronym for Atmospheric Large Aperture Space Telescope, I'm not sure. But in any case, we're talking about 10-meter telescopes that will be built in the future that headquarters is now thinking about. And what they do is they block the light out from the star, let you look at the light from the planet. And if you were to see this kind of spectra here, this spectrum shows, here's the brightness of the planet now, not the star. We're not looking at the star anymore. And you see as functional wave like a nice red curve. That's a black body, so-called. It's just simply a hot rock. It has no atmosphere. If, on the other hand, you saw a dip here, that says A, it's got an atmosphere. B, that atmosphere has CO2. If it's got a dip here, it says that atmosphere has got water. And that's what you need for life, water and CO2. Plants need that to live. If you've got plants, you can generate oxygen. If you generate oxygen, it will photochemically exchange with ozone, and we would see a little ozone band there. So that's what we need to do. We need to build telescopes that allow us to look at the composition of these atmospheres. Bob, how am I doing? Do I have some time?
Yes, you do.
Okay.
Another 10 minutes.
10 minutes. Okay. When we find the composition of these atmospheres, and we find maybe they have oxygen, we're still not going to be satisfied. We want to know more. So what could we learn in a foreseeable future if we continue to develop our technology? One of the things we could imagine is a telescope much bigger than 10 meters in space. I don't know whether this would be 30 meters, like the one that's being built in Hawaii these days, or maybe it would have to be 100 meters. But basically, it's big enough so we see enough light from this planet, which the planets are extremely dim, so that we can look at the reflected light hour by hour from a planet. And so, if we were looking at a planet hour by hour, and it was the Earth that we were looking at from a long distance, we would see it be very low reflectivity, and reflectivity would climb, go back down and do this. This low reflectivity represents the fact the light is now shining on the Earth's ocean, on the Pacific, and consequently we're seeing little reflected light, most of the light into the ocean. Over here, during the day, we're seeing light reflected from the land, and again, some of the oceanic material. If we saw instead something that looked like this blue curve, the blue curve would say that this land mass was ice-covered. This was a glaciated planet. So now we can tell, is it a glaciated planet? If we look here, we saw something like this, which is not quite the same. We're talking about the same shape of land masses here. This would tell us it's desert. The whole planet is essentially desert-like. But what if the planet were covered with vegetation? Well, then it would look like this curve, hour by hour, would look like this. And the vegetation would change seasonally. So now we could say, yes, indeed, this really does have life. Similarly, if the planet had no oceans, we would see this upper curve because it's more reflective. If it was mostly covered with ocean, we'd see the lower curve. If the planet had its spin axis perpendicular to its orbit, there would be no seasons. If it was tilted, it would have seasons. And in fact, these curves tell you what that might look like depending on the tilt of the spin axis of that planet. So from this kind of mission, we would learn the next step of what's on those planets. It still doesn't tell us whether there's intelligent life. And really, that's something far enough in the future that's very likely to be our children's task, or our grandchildren's task, to determine that. So I'm going to stop with a little poem. The poem was sent to us by a Kepler fan, Ray Goodwin. This sort of represents the spirit of what we're doing. The spirit, I think, of all of us that we can all appreciate. Somewhere there are mountains glistening in the snow. Somewhere there are mountains that we shall never know. Somewhere there are rivers flowing fast and free. Somewhere there are rivers that we shall never see. Somewhere there are oceans and sun-drenched island sands. Forests full of creatures in vastly distant planets. Somewhere there's a planet beneath an alien star. The people watch our tiny sun and wonder where we are. One day perhaps we'll find them across the void of space. Perhaps through ways as yet not known. We'll meet them face to face. And good luck to some. Yes, from Ross.
First, a comment. SETI is not projecting anything. It's listening. Maybe there are intelligent beings out there, but they're all listening instead of transmitting. Point one. Point two, is there any hope of resurrecting Kepler?
The Kepler mission used the guide on this group of stars. It used it had force reaction, but 3 of which were required. It lost 2 of those. So the answer is it cannot continue to look at this field of view. But with 2, it can look somewhere else, not quite with the precision. Headquarters is funded the continuation of the mission. It's called K2. K2 is a mountain that's difficult to climb. This is a very difficult mission to perform with just 2 wheels. But it looks at different areas for about 3 months at a time. And it looks for planets, it looks for black holes, it looks for stellar clusters, and it's producing data. It won't be quite the precision, we'll not be able to find small planets, but it's certainly very accurate. And we have to do it for a couple more years. Other questions? Yes?
Is there any technique or process by which you could measure the presence or absence of a magnetic field around any of these planets?
The question was, can you measure the magnetic field around these planets? And now Kepler was a discovery mission. It was low cost, faster, better, cheaper. Just find out, are there planets out there? Because it's easy to prove back 10, 15 years ago that there are no planets. The way you could prove that is if you found some Jupiters in inner orbits, they swept away their small planets. So Kepler was designed to find, are there small planets? That's all it can do. It cannot measure magnetic fields. It cannot recognize atmospheres. It's just this discovery mission. But these future missions might be able to do that. But I don't know how they would do that, even what has been described here. The man in the gray shirt.
Maybe you can clear something up for me. Whenever I hear people talk about the habitable zone of another star, they always refer to it as if it's a fixed area relative to that star. Wouldn't it actually vary based on the characteristics of the planet that might be in it? A bigger planet with the density of Earth would have a thicker atmosphere and a stronger greenhouse effect. So the area where it would have a comfortable temperature would be different than a small planet like Mars. Why isn't the habitable zone defined relative to a specific reference planet?
This describes a little bit of what you're asking. If you look, the habitable zone is curved with the temperature of the star. The habitable zone moves with the temperature of the star. It also moves with the characteristics of the planet. This little white bar is saying, well, if a planet is a little bit to the left of the green bar there, is it too hot? Well, it depends on the atmosphere of the planet. The atmosphere could be very scattered, like Venus's atmosphere, and scatter the light away, so the planet could be in a habitable zone. Similarly, if you move too far away, that atmosphere might be enough to hold the heat in. So the answer is sure. It does depend on the planet and on the star. Gentleman here, the yellow.
Recognizing that Kepler actually exceeded its mission time parameter, it still was so productive. Is there any move on going and repairing the modules that hold it as in stabilization?
The reaction, we fixed the reaction wheels, we fixed the spacecraft so we could do that.
Right.
It's about 5/10 of an AU away. And we used to have an astronaut who worked for us, Janet Voss. And we asked her, you work for us, would you be willing as an astronaut to do a one-way trip to repair those? And she quit. She went back to work for us. So no, the answer is we can't go back and fix
Well,
it.
that's a shame.
It is.
Because it's sitting there in safe mode.
No, it's not safe mode. It's the K2 mission being used to look for planets, but they're not the small planet, not in this area. They're looking along the ecliptic. So look at the K2 mission. Yes?
What about a replacement spacecraft, since it's been so productive? What about building another mission that builds upon this and either is like Kepler or even takes what you've learned and has a few more capabilities than even Kepler had? It would seem like, since it was done as a faster, cheaper, better, that maybe another faster, cheaper, better, similar spacecraft could be done within the budget.
You're asking, shouldn't we have another
Yes.
Kepler mission? Anybody first that motion? Because I'd second that motion. We'd like to do that, but we have these other missions that will explore the nearby stars and get information. And so I'd love to see it done. I think it'd be extremely valuable. But right now, there are no plans to do that, unfortunately. Way in back in black.
So you've got a huge photometric database of stellar brightnesses spanning 3 years in addition to the planetary work. Outside the exoplanet results, what is the most interesting astronomical conclusion that's come out of that data set, in your opinion?
One of the things that has really come from the mission is this enormous data bank on the stars themselves. There's a whole new field, astroseismology. You can look at stars, you can see their ages, you can see their densities, you can see their cores. We have found that in some giant stars where the hydrogen burning has stopped and helium burning has started, we can actually tell what's happened inside the star. And so there's a huge number of people, maybe 1,000 scientists who look just at the stellar data and look at the structure of these stars. So that's a big area that's opened up in astronomy. And of course, we have a huge number of people trying to understand the planets that we're finding. What are they made out of? You know, what kind of planetary system could have formed them? But basically, except for exoplanets, the big object is the astroseismology.
Question, quick one here. What's being done to give these new planets names?
How do we name these planets? Well, you know, the team had to decide that too. We had a team, we had a big meeting. You know, how are we going to name these planets? Everybody stumbled around, you know, things like that. Name them after latitude, longitude, declination, RA. So I said, well, we'll name them Borucki 1, Borucki 2, Borucki 3. Immediately, we got all sorts of good responses. And so we decided we'd name them after the mission. We would name them with a number. And then we would tell you with, you know, like Kepler 62, for example, 62e is the planet that's the third planet out. And we can, you know, so you get that information. It's a Kepler discovered planet. It's the 62nd star that we've labeled. The people, of course, have said they'd like to name all these planets, you know, after their cants and girlfriends and everything they can think of. And so there's an opportunity for all of you to name these planets. And it's part of the IAU. The IAU is looking for possible names, although I don't think they accept names of cats and dogs and whatnot. I prefer, actually, to keep these names because they're in the catalog. We know what they are. We know their information. Wherever you are in the world, you can look them up. And if you want to change the name, contact the people on the planet and ask them what they want to say. Okay, this gentleman's got his fingers up.
Dr. Borucki, we have a question here from our chat room. Using the technology you currently have, can you see a large moon? And if not, how much larger would it, or more powerful would a telescope have to be for you to see these moons?
We looked for the moons. We actually thought at one time that we had found about 30 moons. But we looked through very carefully, you know, does it repeat, things like that. And the answer was no. So we're pretty close to where we need to be. That is to say, the telescope could find Earth-sized planets around the bright stars in short period orbits. As the telescope gets bigger, that means you can find smaller moons, and you can find them around planets that are further away from their star. That is to say, that would show fewer transits. Because usually you find the moon, or would find the moon, near the time the planet transits the star. So if it's far out, it transits the star once a year. You only get one opportunity a year to look at the moon. So, bigger telescopes, closer in planets. So, thank you very much for your time.